So if I want to know how bright a given flashlight is, we have ways of measuring that, right? We can even, forget humans, we can use machines to measure how much light output is coming out of a given flashlight, and that even becomes part of the advertisement of this flashlight. A 400 lumen flashlight might be a pretty bright one, whereas there are a lot of 100 lumen flashlights you can get at the store, and those are a bit weaker, right? So these are different ways of measuring the physical output of a flashlight. What I might ask as a psychologist is a question more like, what about how much brightness a human perceives from a given flashlight or light bulb or something else when we're seeing, right? Just very basic questions of something like vision. So, for example, a psychologist, a sensation perception psychologist might ask something like, can you tell when a 0.01 lumen light bulb has been turned on? Like if you're in a totally dark room and 20 feet away from you, they turn on this tiny dim light. Can you see it? Will you detect it? Right? Maybe some animals can detect it and some animals can't. The question is, can you as a human detect 0.01 lumens of brightness, or is that too dim? What about a 1 lumen bulb or halfway between those? So these are questions we can answer empirically, bring people into a lab and try it out and write down the answers. So that's one kind of simple question we could ask about vision. We could also ask something like, well, what if I double the physical intensity of a light? If I turn it up twice as bright, do you perceive it as twice as bright? Or maybe do you perceive it as 3 times as bright? Or only a little bit brighter despite the fact that I doubled it? Those kinds of questions are answered by sensation perception psychologists in a subfield called psychophysics. This is kind of a common methodology used in sensation and perception, but psychophysics is the study of the relationship between those two things we talked about a moment ago, which is your mental experience, the psychology side. In other words, what you perceive. How bright does it seem? How bright do you see it as? Between that and the physical stimulus. That's the physics, how bright the light actually is in purely physical terms. So the term psychophysics is kind of the combination of those two things, our perception and the things out there in the world, and we study the relationship between those. The father of psychophysics, the person who kind of invented the field or really documented a lot of stuff early on, came up with some clever classic methodology in psychophysics, is this guy Gustav Fechner. And there are others we can talk about, like Weber, I'll mention a little later, but Fechner around 1860 published this landmark Elementar Psychophysik, where he actually coined the term psychophysics. You can find this writing and everything online. It's actually pretty easy to follow. But Fechner came up with methods to answer questions like we asked about light bulbs a second ago. For example, most people expect that when you double the stimulus intensity, like double the light output, that we would perceive it as twice as bright. In other words, we naively expect a linear relationship between the physical reality and what our perception is, the psychology inside of us. But he found a much more nuanced effect. So we usually expect something on the right here. That's kind of the basic view of if you turn the light bulb up, you'll see it as brighter. If you turn it up twice as much, you'll see it as about twice as bright, or some relationship like that. He found something much more nuanced, which is on the right here. Don't worry about the details of this function right now, but basically he found that when he doubled the intensity of a light, it didn't appear anywhere near double as bright, much less so. In other words, doubling the light intensity from 30 units to 60 units, if you look at this little graph here, note that the subjectively perceived brightness doesn't go anything near doubling. So making something twice as bright doesn't mean we'll see it or perceive it as twice as bright. That is an interesting relationship between the psychology and the physics here, psychophysics. So what methods do we use to answer psychophysical questions? For example, how might we measure, say, the faintest light a person can see, or the quietest sound a person can hear, or the least amount of odorant a person can smell, or the lightest touch that a human can feel? How would we actually measure those things? How would we answer that? What are these psychophysical methodologies we could use? I want you to actually take a moment and pause the video and try and think of how you would set up an experiment to answer one of these questions. So go ahead and try that now. Now, those questions, we'll come back to some ideas for methods, how we'll measure that, but those questions are really questions about what we might call the absolute threshold for humans. So for a given sense, something like vision or hearing or something like that, the absolute threshold would be the smallest intensity of a stimulus at which a participant can detect it. You might even say, I've added this little bit in parentheses at the end here, in which a person can detect it some proportion of the time. So why do we say some proportion of the time? Imagine you're an audiologist testing a little kid's hearing by playing very faint sounds to see if he detects them. A lot of people on that last question where I asked you to pause might stop and think, well, yeah, people often measure the faintest sound a person can hear when you go to an audiologist's office. And how do they do it? They just play a bunch of really quiet sounds at slightly different levels and see which ones you can detect. So the problem that we run into quickly here, if you try doing this at home, is what happens, like, if you get someone at a certain sound level saying, yes, they heard it, but like 70% of the time at that sound level, or 40% of the time? What is the actual absolute threshold, the smallest intensity someone can detect? We might define it. We might record the absolute threshold as the sound level that they hear 100% of the time. So only if they get it right every time, if they detect it every time, that is the quietest thing. So the smallest amount of noise that they can pick up every time, that might be our definition of absolute threshold. But then you're missing all of those slightly lower values that the person can sometimes hear, like even 80 or 90% of the time. If the kid gets it right that often, it seems like we've made too high of a bar if we define that as the quietest thing someone can hear. But what if you only record instead the very lowest number, right? The very lowest, the very faintest sound level that kid ever heard even one single time. The downside then is that one time they heard it, you might actually just be recording a trial where they made a mistake or where they imagined they heard something. So that doesn't seem like a very good definition of the quietest thing they can hear, because they might not have actually heard it. So instead, we sort of, we as a sort of heuristic, we often define the threshold as where they detect it 50% of the time. Now, we could use a different number here, and in some cases, we might find it useful to use a different number than 50%. And that's why I said in my definition, just some proportion of the time. But you can see why we don't want to define it as the sound that they can always hear, because then we're missing out on a lot of stuff they're usually hearing, right? But we also don't want to define it as the smallest thing they ever got right once, because again, those might have been false alarms or guesses. So instead, as a sort of heuristic or convention, we often define the absolute threshold as what they detect about 50% of the time. And if there are sound levels or, physical intensities that they detect less often than that, then we can't be convinced that they're really hearing it or really detecting it. And maybe sometimes they are and sometimes they aren't, but we can just define these as sort of below the threshold, below the limit, the limit, right? So subliminal just means below the threshold, below the limit. Now, there are ways we can figure out what someone's absolute threshold is. The ones that Fechner and Weber and all those early psychophysicists came up with over 100 years ago. We're going to go through these as sort of classic psychophysical methods, just a few of these. But the most straightforward one might be called the method of limits. And the method of limits, what you're going to do is present your stimuli in increasing intensity, or on other trials, you might present it in decreasing intensity, and each time just asking the participant to say yes or no if they detected it. So if it was sound that we were measuring, they just say yes or no whether they heard something, kind of like at an audiologist's office. So what you do is on the first trial, you might start at something that's definitely loud enough they'll hear it, and they'll say yes. You get a little quieter, they say yes, 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 a little quieter, they say no. Okay, we'll write that down. Take note of that, where that flip happened at 98.5 or between those two. Okay, but then we want to do more than one trial, because that might have been an accident of that trial. So on the second trial, what we'll do is reverse it. Instead, we'll start at something definitely too quiet for them to hear, and then turn it up a little louder. They say nope, turn it up a little louder. They say nope, louder, nope, louder, nope, louder, and eventually they say yes. And we write down where they flipped. Okay. And then on a third trial, we do the same thing, but with a decrease in intensity. We might get to a slightly different answer this time for various reasons. A given trial might be slightly different, but that's why we repeat a bunch of trials. In the fourth trial, we go back up. In the fifth trial, we go back down. Repeat that over and over. Write down where the crossover, where the switch of their answer was each time. And then after enough of those trials, we just average their answers. So we get the average or the mean of where they crossed over, and that would be defined as numerically, that's their absolute threshold. In this case, 98.5 of whatever those intensity units are. That would be the method of limits. That is one way to measure someone's absolute threshold, to figure out the smallest amount of odorant they can detect, the smallest light they can detect, whatever it is. However, there are some major problems with the method of limits, which is why we don't use it much these days. So one problem is people might just become used to reporting a yes or a no and make that report even beyond their actual threshold where they're actually hearing things. So they might be going yes, 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 yes. And even if at 99 they didn't actually hear anything, they might say yes just because they're like, well, a second ago I heard it and, it's been moving down a little and probably I would hear this. I'm not sure. So if they're not sure, they might just say yes by default there. Or two, they might anticipate that they're near the threshold and make a premature judgment and actually flip to a no before they're actually at a no. They might actually have not heard something here in this second trial, but they'll say yes because they know it's getting higher and they feel like they should be hearing something. So they might prematurely cross over. So this isn't actually a very reliable way to measure where someone flips at. It's not imperfect. Like over enough trials, we're going to get pretty close. So it's not, or it's imperfect, but it's not horrible, but we can definitely improve it. So the best improvement on the method of limits is the second of the three methods we're going to talk about. I'm going to call it the method of constant stimuli. So it's a weird way to name it, kind of a misnomer. Really what we're talking about here is constantly moving the stimulus around, constantly jumping around to in this case, if it was sound, going to quieter or louder sound levels. But it's the same basic idea. You're going to play, if it's for sound, you're going to play a bunch of really quiet sounds or maybe occasionally pretty loud sounds, but you're going to jump around in this case randomly and see whether they detected it. So here in this little graph, you can see sort of as we go through time, this is different trials that we do. The first trial, we might play a sound at 12 decibels. So this is the actual physical stimulus level out there. We played at 12 decibels and asked them yes or no, did you hear anything? And let's say on this trial they say yes, so we've put a little plus there. On the next trial we might, again, randomly, we might jump to 16 decibels and that time they might say yes, no problem hearing that. But on the next trial it randomly goes down to something pretty darn quiet, like 4 decibels, and the person might say no. And the next time we might jump to 8 and they say no, and 18 they say yes, and 6 they say no, and so on. You jump around pretty randomly here. So that gets rid of the problems we had with the method of limits. Now notice here at a given level, like 8 decibels, they might sometimes say no and sometimes say yes. But if we do this over enough trials, we get a feel for, is this yes that they said, is that common? Is that maybe just a false alarm? We don't know, but we can look and find, basically, if we do enough of these trials across enough different levels, we can find where they're getting about 50% performance and define that. The intensity they detect 50% of the time, call that their absolute threshold. And the benefit here is this also means we can do things like throw in the occasional false trial or fake trial where there's no sound played at all, not even a super quiet one, just no sound at all, and see if or when they say yes. And that gives us an idea for their false alarm rate. So we can also take that into account. So this is a more common, this is basically the kind of thing used at an audiologist's office today, a more common, more reliable way to measure where someone's absolute threshold is. The quietest thing they can detect, the smallest, touch they can detect, things like that. There is one other method I do want to mention from the classical psychophysical methods. There are more modern ones we'll run into throughout this course, but for now we're just talking about sort of the classics that people like Fechner came up with. The third one I'll talk about is the method of adjustment. The method of adjustment you can think of as the participant themselves actually controls sort of a dial or something like that. Kind of think of it like a volume knob, although they could also use this to turn up and down the brightness of a light or to turn up and down a touch or a vibration on their skin or something like that. But what you do is you have the participant adjust the intensity up and down until they can just detect it. So in this first trial, the line on the left here, they might start at something that's definitely loud enough they can hear it, and you tell them, turn it down until you reach that point where you can't hear it, and then turn it back up a little till you can hear it. Keep cycling it kind of up and down, just little bits until you feel you're right at the border between, and then press this button. And that's what they do, and we record where it's at when they press the button. But then you have them do a second trial, so we've got this line on the right here, where they might start with the volume knob all the way down, and have them turn it up until they definitely hear something, and then turn it back down until they don't, and then up until they kind of do, and then down until they kind of don't, and get them to where they think they're right there on the border between I can hear it and I can't hear it, and then they press a button, and you repeat a bunch of those trials, take the average, and that would be another way of measuring or defining the absolute threshold, the smallest intensity that someone can detect. So these are the classic ways of finding the absolute threshold. Now, imagine we test someone's hearing or their vision or something like that for their absolute threshold. You might wonder, like, would it look like the graph on the left or the one on the right? In the graph on the left, what we have is at a given intensity, at a given level, they either never hear it or they always hear it. But on the graph on the right here, it looks, some intensities are detected about 20% of the time, other intensities about 80% of the time, and so on. Well, it turns out the one on the right is what we find again and again for all of our sensory systems, for all the people that we test. We always find something like this. Why? That's because at a given intensity level, we may or may not actually hear something. So let's say at the intensity of tone 5, for example, it's very close to people detecting it every time, but sometimes they don't. Why is that? Well, there are a lot of factors about identified, but things like neural noise, so just a bunch of other neural firing that's going on in your brain at the same time, might make it a little less likely that those neurons connect and actually have you perceive a sound, or environmental variables that are there, or momentary lapses in attention, so attention can matter, or just how tired and fatigued a participant is. Did you sleep well that night? Your sensory system might actually not quite detect things. There's also effects like sensory adaptation we'll come back to later in this course, or other factors that can affect this. So because of all that, a particular intensity may sometimes be detected and sometimes not be detected. Thus, our ability to detect is more of a smooth, probabilistic curve than a sudden binary change, a flip from no to yes at a particular intensity level. Often this curve on the right that we find over and over again, this is often referred to as a psychophysical curve. It's an actual empirical measurement of how people's perception changes as we change the physics, the physical stimuli that are applied. Now you might wonder, what are the absolute thresholds for humans, right? If you did carry out these methods and tried measuring this for all the different senses for humans and did it across a bunch of different humans so we can get an average, what you find is, and these are pretty close, I mean this was done back in 1962, but pretty close to same thing we still find today in a bunch of other ways of measuring it. With vision, you can detect a candle flame, assuming you have normal vision, right? Not or corrected with glasses or something like that. But you can detect a candle flame that is lit 30 miles away on a clear, dark night. Now, it doesn't mean you'll detect it every time. What it means is about half the time, if someone 30 miles away from you turns on a candle or lights a candle in their window, about half the time you'll see it and half the time you won't. What about hearing? The absolute threshold seems to be basically for like a standard wall clock. You can hear its tick from 20 feet away if all else is quiet in the room. That would be like about the quietest thing we can detect 50% of the time. For touch, we can actually detect, and again, it differs for different parts of our body, as we'll see later in the course, but a fly's wing falling onto our cheek from a mere centimeter away, we can detect that sometimes. Not every time, but about 50% of the time. What about the smell? We can detect about half the time a single drop of standard perfume diffused through an area that's a volume of like 6 rooms. And we're able to detect a single drop of perfume in an area about 6 rooms spread out, right? Let the air flow around for a little while. And we can sometimes detect that about half the time. With taste, again, it's going to depend on the different chemicals, the different taste qualities that we're measuring. But for sweetness, for example, we can detect a teaspoon of sugar if it's dissolved into 2 gallons of water. But if you dissolve it into 2.5 or 3 gallons of water, you won't be able to tell that whether it's the one that has a teaspoon of sugar in it or the one that doesn't have a teaspoon of sugar in it. But at 2 gallons of water, we get it right about half the time. So that's about the smallest amount of sugar we can detect at that density of sugar. Now, there's a very different question we could ask with these methods of psychophysics. It's not just the smallest thing you can detect, right? Obviously, that's not the only thing we're going to be interested in when it comes to these perceptual qualities that we get from different physical inputs to our sensory system. There are other questions we might be interested in. So here's a different version of this that psychophysics is interested in. I've drawn in front of you, there's 3 boxes, and this little In this little rectangle here, there's a kind of light white box here on the left and a darker gray box on the right. And there's a middle box here. Now, the thing about that middle box is I actually set it to be the exact same color and intensity as the background. So technically, you can't really see. There's not really a box there, right? But my question to you is, how much would I have to adjust that box or that area of the image, making it either brighter or darker before you could perceive it? How much adjustment? What's the minimal amount of adjustment it would take before you could actually see that showing up as different from the background? So that is not a question of absolute threshold. It's actually a different question. It's more a question of how we perceive differences between two things. So we have a different term for that. We're going to call it a difference threshold. Instead of an absolute threshold, the difference threshold is the smallest difference between two stimuli that a participant can detect. And again, I'll say can detect some proportion of the time. Usually, we'll say 50% of the time. So the smallest difference between two things that you can actually tell the difference between them about half the time. This is often called in the literature the JND, or just noticeable difference, because it's such a small difference. Like, it's the smallest difference that you can just tell the difference between those two things. Just tell that that light is a little brighter. Just tell that that sound was a little louder. Just tell that the thing in your left hand is heavier than the thing in your right hand. But where like the smallest amount that you can just detect that about 50% of the time. Now, note, for the difference threshold, we can actually use the exact same psychophysical methodologies that we talked about before. So we can use the method of limits, or even better, we could use the method of constant stimuli, where we jump around to random levels, in this case, random differences, and see when it's different enough for people to say, oh yeah, I noticed it. We could also use the method of adjustment, have them adjust how much difference there is, but see where they actually consistently, about 50% of the time, can tell the difference. That would define our difference threshold. Now, an example of this to help really kind of hammer home what we're talking about here, imagine I was asking someone, can you tell the weight difference between, and in one of their hands I put 200 pennies, and in the other hand I put 201 pennies. So can you tell the difference between 200 and 201 pennies? And if we try this over and over again, what we'll find is no, people cannot do that consistently. What about 200 pennies versus 202? No, people can't do it consistently. What about 200 versus 203 pennies? No, people still can't do it. But as soon as you've got 200 pennies in one hand and 204 in the other hand, people can do this, not perfectly, but about 50% of the time, they will be able to detect that it was different. Again, they might be able to tell you which one it was if they had to guess, or they could tell you, yes, there is a difference versus the fake trials where you did 200 and 200, where there was no difference. They'll start getting it right about half the time here. So you might say, oh, well then for weight differences in your hands, people can tell, they can feel a difference of about 4 pennies. Things just have to be that difference. Whatever 4 pennies weigh, that's the weight difference that humans can detect. Easy peasy. But let me throw a wrench into your plan, or throw a wrench into that. What if I tested, say, 100 pennies versus 101 pennies? Right? 101 in your hands, 101 in the other hand. Can we tell the difference? No, right? Because that's not 4 pennies. And we just learned 4 pennies is the magical weight difference that we can tell. Okay, well, what about 100 pennies versus 102? Can we tell the difference there? You might say, no, of course not. It's not 4 pennies. We know that 4 pennies is the weight difference. And yet when we try it in the lab, when we actually do that experiment, people can tell the difference between 100 and 102. In fact, when we compare 50 pennies to 51, people can tell the difference, even though that's only a difference of 1 penny. And up there earlier, when we tried this before, they couldn't tell that 1 penny was added. They couldn't feel that difference in weight. So it turns out it's more about the percentage. Humans can detect a 2% difference in weight, but not a specific number of pennies. What about something else like light difference? So imagine we're comparing 2 bulbs, right? Put them side by side. Sometimes they're the exact same. Sometimes they're slightly different. People have to guess, are they the same or are they different, and see if they get it right. Or you might ask them, which of these is the brighter bulb, and see how often they get it right. And with a 51 lumen bulb to a 51 lumen bulb, do people get that right consistently? No, we can't do it. What about 50 versus 52 lumens? No, we can't. 50 versus 53? No, but when you do 50 versus 54, yes, suddenly we're able to. So you might say, oh, we can detect a 4 lumen difference. That's the difference threshold for light. It has to be 4 lumens of brightness added before we can tell the difference in brightness. And yet when you compare a 25 to 26 lumen bulb, of course that doesn't work, but a 25 to 27, where you wouldn't expect it because it's not 4 lumens of difference, it actually works. We can detect a 2 lumen difference there when we're comparing to something dimmer like a 25 lumen bulb. The jump of 2 lumens is suddenly now significant where it wasn't before when compared to that brighter comparison unit. So in this case, again, it's a percentage difference that we're able to detect. For light, it turns out it's about an 8% difference in light is required before people can get it right about 50% of the time. What about one more example? What about like shock, being able to detect whether something is more of a shock? Can you tell the difference between 25 and 26 volts of shock? Yes. 50 and 51? Yes. 100 and 101? Yes. But when we get up to a 200 volt shock versus 1 volt more than that, a 201 volt shock, suddenly we can't tell the difference. And that's kind of weird because at 100 volts, you're already at a pretty big shock, and adding 1 volt to that is something we can detect. We can detect a very, very subtle change in the intensity of a shock, but not when we're comparing to a 200 volt shock. Suddenly that 1 volt addition doesn't get detected. So with shock, it turns out we can detect things, again, at a percentage level. In this case, it's a 1% difference in shock. So if we have a big enough comparison, then that 1 volt addition isn't enough. It would have to be 1%. It'd have to be 2 volts added for us to detect it. Now, if we repeat this over and over and over again, as some of these classical psychophysicists did, like Fechner and this other one, Weber, they started to recognize what's going on here with these difference thresholds is that they're always proportional to the magnitude of the stimulus. In other words, they're always like a percentage of the thing we're comparing it to. So Weber actually formalized this as what's called Weber's law. Sometimes you'll see this combined as Weber and Fechner's law, or the Weber-Fechner law, because they both came up with basically the same version, or a slightly different version of the exact same claim here, which is basically we could formalize this with a little equation. Don't worry about the equation for a second here. Let's just look at over here on the right. These fractions, these are the percentages I talked about before. So with light, I told you it's about 8% difference needed before you can tell the difference between two lights. With sounds, it has to be about 5% volume difference before you can tell the difference between two sounds. With weight lifted, it has to be about 2% difference. We saw that before. For tasting something like salt, it has to be about an 8% difference. So again, these proportions, right? 0.079, that's basically 0.08. You can convert that to a percentage by just multiplying by 100. So proportion of 0.08 would be 8%. So these are just percentages, basically. They're saying the percent of change you need in order for you to detect that something is different. That's what a difference threshold is. They're not written as a specific intensity. Rather, it's a percentage of intensity that things have to change for us to notice and detect the difference consistently, about 50% of the time. Now, the formalization here in a formula, you won't have to know this formula per se, but just understand what we're talking about. The fraction here, the percentage, would be this K value on the right. So that proportion, the 0.08 or 0.05 or whatever it is, that's the K on the right here. Then what are these I's? The I is a given intensity. Like, for example, 200 pennies. If our comparison in one hand is 200 pennies, the intensity is 200 for a certain weight, then we'd put in the K, the 0.02 on the right here, and try and figure out up here the delta. That's a Greek letter for difference. So the difference in intensity that we would need to detect, or that we'd be able to detect when compared to a 200 base intensity, all you'd have to do is multiply the 0.02 here by the 200, and that would tell you the difference you would need, how many pennies you would need to add, or the weight of pennies you would need to add in order to feel the difference. So it lets us predict from these fractions, from plugging them in, we can predict for a given intensity how much we'd have to add to detect it. But again, if that formalization is too confusing for you, don't worry about all it's saying. It's literally just saying things are for difference thresholds are in percentages. So as long as you remember that, you've understood the Weber-Fechner law. Now, I do want to mention Weber's law, that thing we just saw. It doesn't hold in exactly every circumstance. It's actually a little bit inaccurate at like very high sound intensities or very, very low intensities. But it's a pretty damn close approximation. It works in almost all cases. And there are attempts to be sort of more universal variations, something called like Stephen's power law or building on that. But honestly, like we're just going to say that's a close enough approximation to understand the lesson with difference thresholds. It's something about proportion or percentage, something like that. At the very least, it's not that simple relationship we might expect like we did with absolute thresholds. But even absolute thresholds, there are some limitations. So even absolute thresholds, like the smallest amount of something you can detect, those can differ a little bit by person. And also they can differ by circumstances. So for example, if your eyes are fatigued or if you have a momentary lapse in attention, that can change how dim of a light you can pick up or how quiet of a sound you can pick up at the audiologist's office. But also things like before and after dark adaptation. So like depending on how long you've been standing out in the dark, you may be able to actually start picking up dimmer and dimmer light. It's not just that things look brighter, but even like things that are right at the borderline of your perception. If you've been standing in the dark for a while, you'll actually see that super, super dim light in instances where you wouldn't have if you had just come out of a bright room. So those are just some caveats I wanted to mention. We'll get into more details when we get into vision really deep later in the course. But the big picture lesson I want us to take away here, the reason we talk about this at the start and this big picture stuff is just it's important to really note and really keep in mind that distinction between physical and psychological. That's really important. So for example, in that light bulb example we talked about before, if we call a single lone bulb let's say a 10 in perceived brightness. So you look at that bulb and you give it some number. You might call it, it looks about like a 10 brightness to me. Then people will call two bulbs a 12 or a 13. In other words, it doesn't seem nearly twice as bright to them, even though we've added literally twice the intensity. So two bulbs are twice as bright, but we don't perceive it that way. We only perceive it as like 20 or 30% brighter. And this has important implications for things like engineering and design. For example, when driving, people may not necessarily perceive a sign as being twice as large when you have the distance it is to that person. So we have to take psychophysics into account to ensure that people see a sign at the distance we expect them to see it at. And that's been important for designing things. And another, just going back to those illusions we saw before, that's really just another application of this big picture lesson where there's a distinction between the physical and the psychological. So the actual physical picture here, right, the distal stimulus that's there on the screen, and thus the proximal stimulus that is hitting your eyes, if you're looking at it in similar context, that stimulus, the physical picture, in this case, for this particular illusion called the Hermann grid illusion, it's just a bunch of straight white lines and black boxes, and there's nothing at these intersections. But if you look around with your human eyes and your human brain processes it, we will usually, most people will say, I perceive at whatever intersection I'm not currently looking at, I will often perceive a bunch of little, or like a sort of grayish or slightly darker area at these intersections. Usually not at the intersection I'm looking at, but at all the other ones in my periphery. That is something we're perceiving, something our brain is adding of how we see the world that isn't there in the picture itself. In other words, that isn't there in the physical stimulus in the world. So it's just another big picture lesson, like our brain adds things that aren't there in the world. It's not always accurate. That is a distinction between the physical and the psychological and why we study these things. Think of it this way. Physically, the electromagnetic radiation that hits our eyes when we see things, that is just a tiny bit of the spectrum of all electromagnetic radiation. This tiny, tiny little bit is all the colors, all the stuff that we can see, what we call visible light, from about 400 to about 700 nanometers of wavelength. That is what humans can detect with their eyes. And yet, that electromagnetic radiation, that whole spectrum, that includes things like radio waves, like AM and FM radio and things like that, but also infrared and ultraviolet light, even X-rays and dangerous things like gamma rays that can cause damage. In fact, right now, as you listen to this, Everyone's cell phone calls are passing through your freaking face all the time. As you're just sitting there, people's cell phone calls are passing through your face. You've got every FM and every AM radio station. All of their signals are just literally passing through your body, passing through your face, passing through your eyes. And yet we don't perceive those things, right? You don't see the radio waves. You don't see the AM station's, signal that's going through, because our eyes' receptors only react to certain wavelengths, what we call visible light. We don't see cell phone calls or radio waves or ultraviolet, but only because we didn't evolve sensory receptors for those wavelengths of light. Our rods and cones don't happen to go off for those. But other animals, like birds and insects, they do. In some cases, they do see wavelengths that we don't. Hell, theoretically, an animal could exist which saw FM radio waves with its eyes. Now, we'll end this first overview topic here, with our quick overview of classic psychophysics. We'll run into more as we get later in the course. But in our next topic, what we're going to do is just take a deep, deep dive into one of our sensory systems, the sense of hearing.